Mhm. Vale, elimino destacado de momento.
Enrique, podemos empezar cuando quieras.
Vale, pues empiezo ya con la presentación. Perfecto. Good morning, everybody. It's my pleasure to introduce Belén. Belén got her PhD at Universidad de Valencia, although most of her work was done in Germany, in Jena. And after that, she moved to Barcelona, starting her postdoc life. And from 2004 to 2007, she was working in the early stages of the Gaia mission, in particular in the framework of the development of a prototype for the processing pipeline. Then in 2008, she arrived at INTA, at CAP, here at Villafranca, where she started to work in the framework of the Consolidated GTC project. This project was an excellent project to coordinate and boost the scientific exploitation of the GTC, of the data produced by the GTC archive. The GTC archive started operation in 2011. Belén was working from 2008 to 2013 in the framework of this project, working for trying to exploiting GTC data. After that, from 2015 to 2019, she moved a few meters away, changing our building from the ESA building, and she worked as external scientific consultant providing services to ESA. In particular, she was working in the development of ESA Sky. ESA Sky is a VO tool developed by ESA to visualize and access different catalogues and images coming from different astronomical archives. In 2020, she moved back to CAP to work in the framework of the Spanish Virtual Observatory project, and since 2022 is a lecturer of physics at the University of Pablo-CEU. For many years, Belén was working in the field of small objects, young, very low mass stars, brown dwarf, ultra cold dwarf. But in the last few years, she also she shifted her interest to other type of stars, in particular AGB star, Galactic AGB star. She has been working in the building of the Gaia Catalogue of Galactic AGB star, which is a collaboration of many partners: the Spanish Virtual Observatory, University San Pablo-CEU, Hamburg Observatory, and ESA. This was a project that was partly funded by ESA, and this project, the catalog of these galactic AGB stars, using Gaia data in particular, is the topic of this talk. So, Belén, the floor is yours. Thank you.
Thank you. Okay. So thank you for inviting me to give this talk today about in the framework of the 20 years of the Spanish Virtual Observatory. Well, we are like a big family at the Spanish Virtual Observatories, and I worked, as you have heard, at CAP for many years, although not here at Torrejón. Actually, it's the first time I'm standing on this stage, and it's quite impressive, although you are not so many people today. But well, the title of my talk you have heard is the Gaia Catalogue of Galactic AGB stars. There are two key terms here, which are AGB stars and Gaia. I will talk about this in a moment. As Enrique has explained, it's a collaboration of several partners. The Spanish Virtual Observatory, which is represented by me at University San Pablo-CEU, and Fran Jimenez here at CAP. Dita Engels from the University of Hamburg, and Pedro García Lario from ESA. And we also had several students collaborating in the project, doing their master thesis or as an ESA trainee, in the case of Juan de Barra from Dublin City University. So as I said, there are two key terms here. The first one is AGB stars. So what is an AGB star? Very briefly, an AGB star is an evolved stage of a star like our sun. So this is the future, or part of the future of our sun. Our sun is what we call a main sequence star. A main sequence star is a star, it can have different masses, different temperatures, different luminosities, but it's characterized because it's undergoing a long period of stability. It's actually the longest stage in the life of any star. And during this period, in the core of the star, hydrogen is being fused into helium, and this is producing a lot of energy, which is radiated mainly in the form of photons of light. And thanks to this, there is a pressure outward that is preventing the star from collapsing due to gravity. So the star is in equilibrium for a long time. Its properties are more or less unchanged, but nothing lasts forever. So eventually, the star will end this stage when there is not enough hydrogen to keep this balance, and it will move to other stages. And what happens from here depends on the mass of the star. So you may think that massive stars will last longer on the main sequence because they have a lot of hydrogen, they have a lot of mass, but actually they also, because of this high mass, they also have a higher gravitational pull. So in the end, they have to burn this hydrogen faster, and they have relatively short lives compared to low mass stars. So the lower the mass, the longer the life of the star. And also the outcomes after the main sequence are different. Giant stars have spectacular life ends. They explode as supernovae, and then they end up as black holes or neutron stars. I don't know if this is. But what we are concerned about today is the life of a star like our sun, which is this evolutionary sequence here. After the main sequence, stars turn into giant stars, then into red supergiant, which is what we call the AGB stars, and then they lose their outer layers. They shine for a very brief period of time as what we call a planetary nebula, which is admittedly a very misleading name because it has nothing to do with planets in principle. And then the bare core of the star remains as what we call a white dwarf. To study stars, there is a tool that is widely used in stellar astrophysics because it allows us to see not just their properties, but also their evolution. That is called the Hertzsprung-Russell diagram. This one here comes from an educational tool, actually, for school children, but I think it's very illustrative. So what we see here is that the vertical axis depicts the luminosity of the star, and the horizontal axis, the temperature. And it's interesting here that temperature goes on the wrong way, so to say. The higher temperature is on the left and the lowest temperatures are on the right. Why it is so, I don't know, but it's always been like this. So when we plot the stars here, we see that the stars on the main sequence, and that's why it's called the main sequence, they are found on this strip here. They spend their happiest period of their lives probably there, and then when they do not have enough hydrogen to sustain this equilibrium, they move out of the main sequence following what we call evolutionary tracks. So what is depicted here in this line is the evolutionary track of a star of 1 solar mass, star like our sun. And when I start the animation, you will see how it moves. The speed of the motion gives an idea of the duration of each particular stage. And here on the right, you see a scale with a 1 solar mass on it. You will see here how the size and the mass of the star change as it moves along the evolutionary track. So we see there are changes in temperature and luminosity, but also changes in mass and size. So let's see if this works. Yes. So now the star leaves the main sequence because the hydrogen fusion is not sustained anymore. The star is not stable. It increases in size, although its core is shrinking, and it becomes a red giant. You can see the change in size is dramatically big. There is also a loss of mass because of the winds of the star, and eventually helium fusion begins in the core, so it stabilizes for a very short period of time, and then the story repeats again. And this is the AGB phase, this second giant star phase. Let's see. Go forward without starting the video again. Yes. So what are the properties of these stars? They are very cool. They are called red supergiants because of their surface temperature is very low for a star, which is around 3000 Kelvin. They have high luminosities compared to our sun. They are thousands to 20,000 times more luminous than the sun, typically. They are also characterized by strong winds and strong mass loss. There are outflows of matter from the star. There are very strong winds, much stronger than in our sun. You know the sun has winds. And because of this, they are very bright in the infrared because of the cold temperature and all the dust and gas that is surrounding the star, but they are often opaque in the visible. This is one of the main problems that we have. We don't actually see the star. What we are seeing is the envelope of gas and dust that is covering the star completely. So this is how it looks like from inside. We have the core, which is inert. Now it's not fusing any gas, but still there are some layers on top of this inert core that are still fusing, but not at enough rate to maintain a balance. There are convection cells and the stellar envelope that mix the material and bring material from the core upward. And we have a stellar atmosphere where grains are forming, like very small grains of sand or chalk. And most of this material escapes outward, creating like an envelope surrounding the star, what we call a circumstellar envelope. There are outflows of matter in the form of strong winds. And there are also what we call masers, which are similar to lasers, but in the microwave domain. So there are lots of things here going on. And in this period, as you have seen in the animation, the star loses a lot of its mass. Another thing that characterizes these stars is that they pulsate. Their size and their luminosity vary with time. This is a representation of what we call a Myra variable, which is the prototype. Myra is the prototypical star for this type of variation. It's characterized because the periods of variation are very long, from hundreds to thousands of days. And the amplitude variations are also very high. They have several magnitudes. I don't know how many astronomers are there in the room, but astronomers usually express the brightness of a star in what we call magnitudes, and it's also a reverse scale. First magnitude means the star is brighter than a second magnitude star, and so on. And it's a logarithmic scale compared to the physical luminosity. So several magnitudes means a very high change in luminosity, several orders of magnitude change in luminosity. One thing that has been proposed for these stars, because we see they come in two flavors. We have stars that when we observe their spectra, they are rich in carbon, and other stars are rich in oxygen. They do not have carbon in their spectra. And it has been proposed that this is related to the mass of the stars. So intermediate mass stars would have carbon, low mass stars wouldn't have this carbon on the envelope because the processes inside the star are not strong enough to bring the carbon upward to the outer layers. And in the highest mass stars, this carbon mixing would be inhibited by other processes. So the carbon would combine with other molecules and disappear from the spectra, and they would be oxygen rich again. These high mass stars are also associated with the mesas that I was mentioning earlier. So in particular, what we call OH mesas that are related to the OH molecule. But this is not clear that it's actually happening. This is based on observations on the Magellanic Clouds, which are, as you know, are the satellite galaxies of the Milky Way. But some recent work on AGB stars on the Milky Way has not been able to prove that this chemical branching is indeed applicable to our galaxy. So this is one of the things that remain open. The masses you have here are masses for a star like our sun in terms of chemical composition. They can change a little bit depending on the chemical composition. So now that we know, I hope, more or less what AGB star is, let's focus on the motivation for this work and the goals of the project. Why is it interesting to study AGB stars? Well, they are an important step in the stellar structure and evolution. And in particular, they are telling us things about the future of our sun. We won't be here to see it, but our star will eventually become an AGB star. Also, because of these strong winds that I was mentioning, they contribute to enrich the interstellar medium. The space between stars is not empty. There is some very low density gas and dust there. And initially, at the very beginning of the universe, this gas and dust was essentially hydrogen. With the processes that are happening in the life cycle of stars, new molecules, new elements are being built, and then they are released to the interstellar medium. So the interstellar medium is no longer just hydrogen, but it has a mixture of different elements and molecules, and this is what we call the ISM enrichment. ISM stands for interstellar medium. So it can give us hints into the chemical evolution of the galaxy, the chemical history of the galaxy. And it has also been proposed that they could be used as distance tracers. If you know something about astronomy, you know that distance estimation is one of the biggest problems in astronomy. There are many parameters that cannot be determined without knowing the distance to the objects, and it's not an easy task to estimate the distance to things that are billions or billions or and billions of kilometers away. So there are different techniques for this. One of them is to use objects whose luminosity, whose light output is known from other observations or from theories, and to compare this luminosity with the apparent brightness that we actually measure for the object. So in this way, we get an idea of the distance, and we can apply the same distance to all objects that are nearby. This is what we call a standard candle. A very typical standard candle that has been used for more than a century is what is called a Cepheid variable. It's another type of variable star that has a relation between its luminosity and its period. So measuring the period of variation of the stars, we can know how luminous they are, and comparing this luminosity with the apparent brightness, we can know how far they are. And it has been proposed that the same could be applicable to Mira variables, to AGB stars that show this long-term variation that I was explaining before. This would be useful to better understand the galactic structure, the structure of the Milky Way. And here we face a problem, and it's also related to distance. Most of what we know about AGB stars, most of our theoretical model of AGB stars is based on observations outside the Milky Way. It's based on observations in the Magellanic Clouds. And this is because when you have something so far away as the Magellanic Clouds, you can assume that all stars are at the same distance. And this distance is still close enough so that you can resolve the stellar populations. But inside the Milky Way galaxy, there are relatively few stars with accurate distance measurements, relatively few AGB stars. So, or this was true until now, until Gaia was launched, which I will talk about in a minute. So what our goal was to use Gaia, as I will explain later, to build a large sample of AGB stars in our galaxy with accurate distance estimations so that we could derive the luminosities of these objects and their masses and study these theoretical models of AGB stars and see if they apply to the Milky Way. So for that, we're using Gaia. Probably you have heard talks of Gaia here before because it's dominating astronomy in the last year. Gaia was launched in December 2013 and began in its operations in July 2014. And it has been operating until the beginning of this year. It's a mission that has been scanning the whole sky repeatedly to build an atlas of stars in the galaxy with accurate positions, distances, motions, and also deriving stellar parameters, properties of the stars. The amount of data that it is producing is huge. Now we have the third data release of Gaia available. In 1 year and a half, we will have hopefully the fourth data release, and it's not going to be the last one yet. And since the first data release, it has changed our picture of what we thought we knew about many objects in the galaxy and also outside the galaxy. So Gaia does a lot of things. It uses essentially three observing techniques. The first one is astrometry. And here we are mostly interested in distance estimation. And also it provides also photometry, that is measures the brightness of the stars in particular ranges of the electromagnetic spectrum. Gaia observes in the visible range, and it provides broadband photometry in 3 filters, one that is very broad and covers most of the visible light spectrum, and one that covers only the red part, and another one that covers the blue part of the spectrum. And here it's very important, the brightness changes, the variability studies, because as I have already repeated several times, these stars are highly variable. So the technique that Gaia uses to measure distances is a technique called parallax. It's not new. The basic idea comes from the time of the ancient Greeks, and it's based on trigonometry. It's based on the idea that when you shift your vantage point and you look at a distant object from 2 different vantage points, this object seems to have shifted with respect to other objects that are in the background. So by knowing the distance between the 2 observation positions and measuring the angle of this change, you can know how far away the thing is. Applied to stars, we use the orbit of the Earth as our baseline, we take 2 extreme distances inside the orbit of the Earth for our observations. And as the Earth moves, you can see that the star does a motion like this. This is very exaggerated, and the actual motion is very small. And difficult to measure. The farther away the star is. So small parallax means a big distance. This shift is called parallax. So before Gaia, the best parallaxes that we had had a precision of milli-arcseconds. 1 arcsecond is 1/60th of 1 arcminute, and 1 arcminute is 1/60th of 1 degree. Now with Gaia, we have precisions of micro-arcseconds. So the improvement is remarkable. And with this means we can estimate distances to objects that are much farther away. Still, this is still keeping observing things inside the galaxy and at a relatively nearby region around the sun. So how do we build the catalog? We took advantage of the Virtual Observatory for this. I'm not going to explain a lot about the Virtual Observatory because I assume you already have several talks about this, but you know it's a an initiative to share the data that are available and spread over the world in different astronomical archives. They define common protocols for the preparation of this data and for the retrieval of this data. And there are dedicated tools that use these protocols to access the data so that you can sit on your desk and with just one application access archives worldwide and download all the data you need. So this is here on the lower part of the slides. Now will appear the different tools that we use and services. There are some data services like ESA or CDS or Received or the Gaia Archive. And there are also tools for analysis, which are the ones on the left. What we first did was to compile a list of candidates for AGB stars, and we took advantage of what was already available in the literature. One of my collaborators, Dita Engels, had developed a database of sources with OH masers. Many of them are AGB stars, and there are also other objects that emit OH masers. And here we had nearly 3,000 candidates. We expected these candidates to be, if they are really AGB stars, the most massive AGB stars, these oxygen-rich AGB stars that I called OHIR stars earlier. Then for the other two types of chemistry branches, we took a paper by Su from the year 2021, where he made a compilation based on previously published works in the literature of carbon-rich AGB candidates and oxygen-rich AGB candidates. You can see the numbers there. There's a huge amount of them, and we only took the samples that were best fitted for our purposes. And then we cross-matched this catalog, these compilations with Gaia to get objects with Gaia counterparts. This sounds easy, but you have to be careful because the coordinates in these compilations are sometimes quite inaccurate. Sometimes they are very old surveys that have not had a follow-up later, or they come from infrared or radio observations that quite often do not have the same precision as in position as optical observations, visible light observations. So if you just do a blind cross match, you can have lots of wrong matches. So we decided to be careful and go step by step, refining the coordinates in the process. So first, instead of going directly to Gaia, what we did was to cross match with a mid-infrared catalog called Allwise. In this way, we already had some infrared counterparts of our sources, but we also had better coordinates. We use these coordinates then to cross-match with another infrared catalog, but this infrared catalog observes, has photometry at shorter wavelengths, closer to the visible range, called 2MASS. And with these coordinates that are a bit more accurate than the WISE coordinates, we did cross-match with Gaia DR3, and this is the result. So from the starting point, our number of sources were obviously really reduced, but what we want in the end is a clean sample and not having many intruders in our list. So this is to give you an idea of the difficulty. We visually inspected using ESA Sky, the tool that I was working with, Enrique mentioned another tool called Aladdin, which is where this snapshot comes from. We inspected visually all the matches to make sure that we were getting the most likely correct match. You see across on some of the images, these images display 4 different surveys. The 2 on the top are optical surveys, invisible light. One is a very old survey called DSS2, Digital Sky Surveys. The second one is called Pan-STARRS. It's more modern and it has better resolution and is also deeper. It reaches fainter objects, but it's not complete. It does not cover the whole sky. That's why we're using both of them. And on the lower panel, you have on the left a 2MASS image from this two-mass survey that I was mentioning before, and the other one is a WISE image. And the color dots indicate the positions of the sources from the different catalogs. Red is for WISE, green is for two-mass, and blue is for Gaia. Gaia does not provide images. That's why we cannot use the Gaia images, which would be nice, but it's not. So the cross in the middle indicates the input coordinates from our starting point, from our compilations. And if I were to take blindly the Gaia source closer to this position, I would take the blue star that is there next to the cross, the blue from there, and end of the story. However, it turns out that the actual AGB star is this one here. It's difficult to see in the WISE image because the two stars are blended. They are a bit more separated in two mass, but in the visible light, we clearly see that there are two stars there. And the right one is the one on the top, not the one on. So that's why we decided to go step by step. First, find the WISE counterpart, then find the closest two mass counterparts, inspect them visually to see which one is more likely to be the AGB star, and then take this one and do the cross match with Gaia. Because otherwise we would get lots of wrong matches. The search radius was also decreased as we were improving the coordinates to avoid having many interlopers in the search area. So after this, we had a sample of stars with Gaia counterparts, but Gaia, the main Gaia catalog, does not itself provide the distances. It provides the parallaxes, and you have to compute the distances from the parallaxes or just look for somebody that has done it for you. So this is a paper from the Gaia DPAC, the Gaia Data Processing and Analysis Consortium, where they did, following a statistical approach, they already did this job and provided distances for the majority of objects in the Gaia DR3 catalog. We also applied some quality criteria because if you work with data, you know that data sometimes have different quality. And in the case of stars, this is critical. So first we impose that the parallax value was positive. A negative parallax value doesn't have any physical meaning, but because of the automatic computation of the pipeline, sometimes we do have negative parallax values in the catalog. Then we imposed that the relative error of this parallax measurement was 20%. This may seem a bit high for people working in other fields, but several studies suggest that this is a good threshold for AGB stars. And we also imposed the astrometric excess noise, which is a parameter that Gaia provides for gauging the quality of the astrometry, was lower than 1.5 milliarc seconds. Then for those sources that had a distance available in the catalog, for the sources following this, fulfilling these conditions that had a distance available, we used another work that provides an extinction map. What does this mean? Well, we have, as I said, there is interstellar medium between the stars, and this interstellar medium absorbs part of the light. So stars that are far away are dim not just because they are far away, but also because there is material in between that is absorbing the star. Depending on where this star is located inside a galaxy, this extinction problem will be more or less dramatic. And in our case, since our stars are shredded in dust themselves, this extinction is expected to be much lower than the extinction from the circumstellar envelope, but still it has to be taken into account if possible. So we use these extinction maps for the stars with known distance to get the extinction estimation. And then we had a subsample of what I will call in the next, the following, the good parallax sample with a limited number of stars with parallax. You see, this can seem a bit depressing because we had thousands of stars and now we have hundreds of stars with parallaxes, but so it's life. It's much better than what was available before anyway. So what was the next step? we were not happy with this. We had Gaia data that was nice, but we wanted to estimate the luminosities of the stars if possible, if distances were available, or at least the overall flux of the stars. And for this, we needed more data. We needed more photometry so that we could build what is called the spectral energy distribution of the stars. So we use for that a tool called VOSA that is developed by the Spanish Virtual Observatory here at CAP, that allows you to very easily retrieve photometry from lots of catalogues in the Virtual Observatory and build plots like this one here, where we have the flux of the star over the wavelength of the light. H dot is the flux integrated in a filter, in a band with that central wavelength. And the different colors and shapes give you an idea of the amount of catalogues that we were using for building this type of graphs. So each color represents a different survey. As you see, there is like a broad maximum, and this is what we expect in an AGB star, to have a broad maximum in the infrared. But there were also some objects that didn't show this behavior, and we could exclude them as interlopers in our catalog. The next step was to fit these SEDs, these spectral energy distributions, with theoretical models for AGB stars. This is the gray line and dots that are depicted on the graph. They are the synthetic photometry according to this model. And for those sources that were well fitted were kept as likely AGB candidates, and the other ones were rejected. So this way, using this fitting, we could integrate the whole flux and find what is called the bolometric flux of the star. And in the case of those stars with a known distance estimation, we could then find their luminosities and identify sources that were there, but were likely not AGB stars. So our sample was a bit more reduced thanks to this. And still we were not happy, because you have seen the SED of the AGB star, but there are many other astronomical objects that also have similar SED shapes. The fact that the object is well fitted with an AGB model does not actually ensure that this object is an AGB star, because we can, for example, we have this uncertainty in the distance that can make objects look similar even if they are completely different, because we think they are closer or far away than they are. But fortunately, we have a big literature database and a big object database in astronomy that is called SIMBAD. SIMBAD provides identifiers and information from many astronomical objects, and the majority of our objects were there. So we used SIMBAD to filter out interlopers. So let's say an object with an OH maser could also be a young stellar object, a young star. How can we know this? If there are 100 papers saying that this is a young star, this is probably a young star. I mean, 100 people cannot be wrong. It's much more likely that I am wrong. If there is few information, we kept the object as a possible candidate. So in the end, this is our final catalog. Actually, the final numbers are only for the OHIR star, because we are still refining the work with the other two samples. But you can get an idea of the amount of stars that we have and the amount of stars that we have with luminosities and distances. So this looks like a lot of work, but it's really very easy to do when you have the Virtual Observatory tools available, because very comfortably you can access lots of data, and they cannot all be combined in an homogeneous way. So what are the properties of these stars? Do they fit what we were expecting from AGB stars? So first, let's have a look at the sky distribution. I explained earlier that the original compilations were compilations from works in the literature. This means that they are not homogeneous. People may have a trend to observe particular regions of the galaxy and leave out other regions for whatever reasons, maybe technical, maybe just a matter of preference. So the distribution was not expected to be homogeneous. It's also not homogeneous because what you see on the horizontal central part is the galaxy disk, and this is a plotting galactic coordinates, and above and below, well, the galaxy is not completely flat, but quite flat. There are less objects. The blue dots represent the carbon stars. You see that they extend farther in the sky than the green and red dots that are the oxygen stars, the oxygen-rich stars. This is also related to the fact that we are taking sources that have been detected by Gaia in the optical, and carbon stars are brighter in the optical as a general rule than oxygen-rich stars. So that's why we can see them more distributed. And also because these oxygen-rich surveys have focused more on the central part in the solar neighborhood or close to the galactic center. In the galactic center, maybe if you have good eyes, you notice that there is like a hole. That's because the density of stars is so high in that region that it was impossible to assess the reliability of the matches. When we looked at these different surveys, we couldn't really distinguish between different sources. So we decided that it was better to leave it out than to have a lot of contamination in our catalog. For the sources with parallax, we can see how far they extend. This is the histogram on the top, showing the distance distribution. Again, blue is carbon-rich, red is OHIR, and green is massless or rich stars. You see that the carbon-rich stars extend much further. This is also because they are bright in the optical, and we can then have better measurements of them, and they have, in the end, better parallaxes and then distance estimations. And the others, well, are confined to a closer area surrounding the sun. So in the end, especially for the OHIR stars, we are tracing a local sample of stars. The distribution below is a luminosity distribution in solar luminosities. And it shows more or less what we expected. The majority of these stars have luminosities of several thousand solar luminosities. There are a few that have very high luminosities. In some cases, we have to check distinction correction to see if this luminosity is real. In some cases, they can be interlopers. So red supergiants that come from the evolutionary path of more massive stars. And this is the equivalent for Gaia data of the HR diagram that I was showing earlier, where I was showing the evolution of a star like our sun. Instead of temperature, what we have plotted here is color. This is an index that is done by subtracting two magnitudes. One bluer magnitude, take the observation of the flux in a bluer filter and one in a redder filter. These are the blue and the red filter from Gaia. So the bluer the star, the more to the left in this diagram, and the redder the star, the more to the right in this diagram. And on the vertical axis, we have what we call the absolute G-band magnitude. The G-band is this band covering most of the visual part of the spectrum in Gaia observations. And absolute stands because it has been corrected for distance. So what we have here are only the objects that have a measured distance, and the objects with parallax. And we have corrected the observed flux with this distance to get the absolute flux. The gray dots represent the main sequence, the big sequence in the middle. Here, this is the red giant branch, so the first stage in the evolution of a solar type star after the main sequence. And this other sequence below is the white dwarfs. And our objects are the color dots on the top. So they appear where we expected them to appear, above the main sequence. It's interesting to see that, again, there is a separation between carbon-rich and oxygen-rich stars. The blue dots, the carbon-rich stars, are bluer. They are hotter than the oxygen-rich stars. And it's also interesting that we do not see a difference in whether the oxygen-rich stars have major emission or not. I said earlier that this chemical branching model suggests that the most massive stars would have OH masers, while the less massive stars wouldn't. And that would be a distinction between oxygen-rich stars linked to their mass. But here we don't see any difference between the two populations. Gaia also provides photometry, as I mentioned, and it provides epoch photometry. So what we were seeing in the HR diagram was the integrated flux, the average flux over the whole period of observations. But here we can also take these epoch observations, these individual observations, and construct what we call the light curves. We plot the flux over time, essentially, and we see how this brightness is varying over time. There are some sophisticated techniques to extract information from this. And what you see at the left is what we call a periodogram that analyzes the data and tries to extract the most likely period. In this example, the period is 500 days, which is something quite typical of a Myra variable. And on the right, we have the folded curve, which is when we have like folded literally all the data to show the amplitude variations over time. And we see that there is a change in about 3 magnitudes in this case, which is a big change in brightness for a star. Again, this is also typical of Myra variables, which was expected for AGB stars. If we compare the periods and amplitudes for the 3 different samples, we can produce a plot like this one. We have period on the x-axis and G-band amplitude on the y-axis. And we see there are clearly 2 types of objects here. First, we have these objects that have high amplitude variations and are Myra-like variables. You can see that nearly all the green and red dots are in this part of the diagram, and only some of the blue dots are here. So almost all the oxygen-rich stars in our sample show Myra-like variability, and only 56% of the C-rich stars, more than 1/2 of the carbon-rich stars, show this type of variability. Below, we have variability with also very high periods, but with very low amplitudes in comparison, and that is not so regular. These are called semi-regular variables. And here we have very few oxygen-rich stars and 44% of the carbon-rich stars. Another interesting thing is that, again, we see no difference between the 2 samples of oxygen-rich stars. Whether they have masers or not, they are located in the same area of the plot. This is shown as an histogram. First, we have the period histogram on top, where we see that the periods are indeed very similar for all 3 samples. And in the lower part, we see the G-band amplitude distributions, where this gap between the carbon-rich and the oxygen-rich is more visible. And there was also a separation in the previous diagram, but here it's obvious that there is a separation in the peaks of a bit more than 1 magnitude. But again, the difference between the 2 types of oxygen-rich stars is not obvious. This was done with the stars that have an accurate distance estimation. So we can say, well, maybe this is because there is a change in the luminosity. Overall, we saw that there is not a difference in luminosity between the 3 samples, but maybe when we have accurate distances, the picture changes. But the truth is that this is not happening. You can say, okay, but you had very optimistic estimations. You took 20% of relative errors. Okay, let's restrict it to 5%. Still, we don't see any difference. So this is still a work in progress. We're trying to understand what is happening there and what are the implications for the current model of AGB stars and what the evolution of AGB stars. But in case you are curious, you can also get the data, because that's the spirit of the Virtual Observatory, that anybody can get the data and do whatever they want with them. We have built a public archive that can be queried online. This is the page. It's not yet public. It will be public very, very soon. Here you can query for now just the sample of OH-IR stars. We will be including the other samples in the future. You can query and select objects depending on the parameters that you are interested. You can download the table. You can also download the whole photometry to build the SED with the tool you prefer. You can download the SED plots. And in a future stage, we will also add the variability light curves. What I've been telling you today is going to be published in a series of papers. The first one was accepted just last week. So we're very happy. We have 2 more in preparation. So the first is presenting the sample of OH-IR stars, and some of the data are also retrievable through the CDS, the Center of Astronomical Data in Strasbourg, in France. And we are preparing 2 more papers. We're currently writing them for the carbon-rich stars and the oxygen-rich stars without masers. And there are 2 more papers planned, at least, one for the variability studies and one to try to bring all these pieces together and to get the whole picture of the subject. The project has also yielded 2 master theses. One was directed by Fran and me, and the other one more recent by Pedro García Lario from ESA. So just to conclude, what I would like you to take away, especially if you are not astronomers, is that an AGB star is a late evolutionary stage for stars of mass similar to our sun, characterized by high infrared brightness, high optical obscuration, strong mass loss, and high long-term photometric variability. So if you can just remember this from this talk, it's fine. If you are an astronomer or are more interested in astronomy, then I would like you to take away more things, obviously. Using Gaia DR3 data and Virtual Observatory tools and services, we constructed a clean catalog of galactic AGB stars, including both stars with oxygen-rich and carbon-rich chemistry. We built the spectral energy distributions of the sources and fitted them through theoretical models, so we could derive their bolometric fluxes and their luminosities if a distance was available. We analyzed the Gaia light curves for our sources and found that there are 2 types of variability: Myra-like variability, that is high amplitude, long-term, long period variability, and semi-regular low amplitude variability. The vast majority of oxygen-rich stars belong to the first group. They are Myra-like variables, but only half of the carbon-rich stars belong to the Myra variable sample, and the other ones are semi-regular variables. And the last thing is that the oxygen-rich stars with and without OH maser emissions show very similar properties, while the carbon-rich stars differ only in optical colors and variability amplitude. So at present, we cannot confirm the chemical branching scenario that was proposed from the studies in the Magellanic Clouds. And with this, I reached the end of my talk. So thank you for your attention.
Thank you so much, Belén, for your talk. We have some minutes for some questions. So does anybody?
Thank you very much for the very, very clear talk. So my question was related with the last item in your conclusions. Indeed, I wondering how well established is the chemical branching scenario that you mentioned at the beginning. So classifying them in terms of the mass, essentially, right? So what I see is that your classification partially support, but not fully support the scenario. So can you expand more about this?
As it is written here, it was established from studies in the Magellanic Clouds. And some recent work on the galactic AGB stars actually already challenged this picture. One important difference between the Magellanic Clouds and the galactic AGB stars is what we call metallicity. I hope there is no chemist in the room because it would scream. What we call metals in astronomy is anything that is neither hydrogen or helium, which I know it's not a metal from the chemical point of view, but it's a metallicity. In short, it's an idea of how purely hydrogen is that star or not. So the metallicity in the Milky Way is higher than in the Magellanic Clouds, and this can affect the evolution. So this is one of the reasons why maybe we don't find the same results. But another reason we cannot find the same results maybe just be that we are actually not tracing the lowest mass objects. We are only tracing highest mass objects that are actually not displaying masers for whatever reason. So it's still a matter of high discussion in the group what this actually implies.
Okay, thank you. Does anybody have more questions?
Yeah. Can you? Yeah, thank you for the nice talk. So my question is related to these to the physical properties you found and the distances. So you found OH masers more in the center than OH rich and carbon rich, right? If I remember correctly. So this was not known, right? Until now, the difference of the population of these AGB stars with respect to the distance.
But this is biased because of the surveys that were used. So you cannot really extract conclusions from that. So it can't just be that people focus more on the galactic, in the central part of the galaxy to study masers because they found it easier.
Okay, this was my question. Okay, thank you.
Thank you. Any more questions in the room? And what about in Zoom? Okay, so thank you very much, Belén.